Okay, so welcome to week 5. We're going to take what we learned in week 4, we're going to take that notation and we're going to do new things with it this week. We're going to move on to more complicated operations. But for this launch, let's go back and revisit matrix vector multiplication. And what do we have here? We want to compute y becomes a times x plus y. And what I've done is I've put a concrete example up here, right there. And we had 2 algorithms for computing this. And the first algorithm would do so by rows. And how would that algorithm operate? Well, it would go, let's say there's a top part and a bottom part here. Let's identify the top row. Let's do inner product adding to the current element of the vector, which then would change this element right here to something else, and then it would move on etc. Okay? Now, one question is, how easy is it to take the algorithm as we express it, using slicing and dicing, and translate this into, say, MATLAB code that just uses indices? Well, let's think about that a little bit. Okay? Typically, we use the index I to indicate in which row we currently are. And typically, we use the index J to indicate in which column of the matrix that is involved we currently are. So we have an index I and an index J. And notice if we pick our index I to operate with the current row of the matrix, then that means that it also is operating with the current index of Y. And remember, this is Y as it's being overwritten, and here we have the original Y. How would we then translate this into MATLAB code? Well, in MATLAB, you probably wouldn't use a while loop. You probably would use a for loop. So you would say, for every element in Y, what we need to do is take a dot product of the corresponding row with the vector x, and then add to that the entry in Y. Okay. So the way he would translate that is to say, okay, for I is equal to 1 through n. And notice that we're going to be dealing with symmetric matrices shortly, and therefore the number of columns is the same as the number of rows, and therefore I don't have to think about m versus n in terms of the row versus column size. Okay, so we say for I equals 1 to n, and then you would need to do the dot product, so that would give us a loop for j is equal to 1 to n, and then you would have an end, and you would have an end. And what would be the update to y that would come in the middle? Well, you're just updating y of I with a of I comma j times x of j added to y of I. Okay. Now, let's move on. What if we know that this matrix is symmetric? And if you need to, go and review what it means for a matrix to be symmetric. This matrix is symmetric. Why? Because entries reflected across this diagonal equal each other. If the matrix is symmetric, then we should only have to store half of the matrix. So what if we chose to only store the lower triangular part of the matrix? Something else may be above the diagonal. It may not be stored. It may be that we don't want to access it. Whatever. So we'll put stars there. Now notice that the entries above the diagonal are stored, they're just not stored in the natural place. What I want you to do is do the exercise of changing this MATLAB code, this MATLAB program, from one that just deals with it as if it's a general matrix to one that deals with it taking advantage of the fact that the matrix is symmetric and only the lower triangular part is stored.